Stop talking, yeah. Run out of the room. Yeah, thanks.
Welcome, everyone, to the first Center for Artificial Intelligence Decision Making and Action, or CAIDA, research seminar. So this is our, we're going to have several different seminars sponsored by the center at UBC. There's going to be one on AI applications, and there's going to be one on AI and ethics. And this is distinguished from those other two series by being focused on technical problems in the core of AI. So what you can expect from this seminar series is something like what you would get from a keynote talk at an AI conference. So it's going to be talking about technical work in AI with the intention of being accessible to a broad AI audience, but not shirking away from technical details. I think we're going to be experimenting between two different foci in this kind of seminar series. We're going to try to decide whether we like it better to have two 20-minute talks or one 45-minute talk. I think we're going to try both formats for a little while and see where we end up. I should say this seminar series, I'm the director of CAIDA. I am not in charge of this seminar series. Rather, David Poole and Jim Little have graciously volunteered to organize it. And ordinarily, I would have David be the one speaking to you right now, except that he's also one of the speakers, so he might seem self-interested in introducing himself. So for today only, I'm the one saying hi to all of you. But our first speaker is Kieran Campbell, who's a postdoc in statistics and also molecular oncology. So he's a great example of the breadth of disciplinary areas that we have within CAIDA, and I'll turn it over to him.
Great, thanks very much. Firstly, how is the volume on the mic? Can everyone hear me, or does it need turned up a bit? Good? Good at the back? Perfect. All right. Well, thank you very much for the invitation to speak here. I am Kieran, as said before, working in a few different places around UBC. I'm going to be talking about this project that's actually fairly new, about sort of sequential feature acquisition. Mainly in the context of medical diagnostics. It actually came out of an idea about how to design websites and website interfaces, but found a very much better home in how to do sort of optimal acquisition if I'm trying to do diagnoses. I was going to talk a bit about what else we work on, which is statistical data integration in genomics. So we spend a lot of time integrating things at the single cell level. But I ran through the slides earlier, and I went way over time when I included that. So we do that as well, and we have some papers and stuff. Anyway, onto this problem. This is a very applied sort of reason for looking at it, although we get sort of into methodology quite a lot. But the basic question we're asking is, what lab test should I do next to make a diagnosis? So imagine I'm in a hospital, I'm in an ER room, and I get a patient comes in with lung infection or lung pain or whatever, and I want to ask, well, what's the optimal test I now send for in order to make the best diagnosis I can possible? So consider the scenario. So your patient comes in here, lying very, very ill in their hospital bed, and they have chest pain, and I have a few candidate diseases in my head I'm going to diagnose them with. And I know I can send off for some lab tests. So I can imagine I send them off for this blue lab test. And if that came back positive, I'd have this sort of posterior over disease diagnosis that's very uniform. So it doesn't really tell me anything, right? This is in the top right here. I don't think my pointer is working, but I'll do my best to describe. Or I could send them off for this sort of pinky color test, in which case, if it tested positive, I would know fairly certainly that they had disease number 1, and I would rule out diseases 2 and 3. Or I could send away for this red lab test, and I would rule out disease 1 and have fairly even a posterior belief that they had diseases 2 or 3. So you can see I can build an intuition here, right, that I really don't want to go for a lab test blue. I want to choose one of the other ones. And then there's a question, well, which one do I want to choose? So the setup we're looking at here is how do I choose the next lab test in a way that's optimal to help me get to this diagnosis or help me have the most informative posterior distribution over possible outcomes? And this applies in quite a lot of inference setups where the measurements are expensive to perform in sequential. So I don't want to go out and do every possible lab test. I want to do one after the other until I'm fairly certain I've arrived at a good diagnosis. And this is the second point, is that I'm going to perform my sort of final inference, my final guess or diagnosis of this patient's disease before I've measured every possible lab test. You know, when you turn up at a hospital, you don't get sent off for every possible test. You do a few, and then the physician is fairly fairly sort of convinced that you have a particular disease. So this is the setting we're in, and the sort of background to this is I already have some model linking diseases to lab tests, right? So I've already done inference in some way, maybe from an epidemiological study, maybe from clinical studies that makes this link. So I'm just going to formalize the sort of mathematical notation and setup for the rest of the talk. So what I'm really interested in is this posterior predictive of some class or cluster labeled Z. Traditionally, in machine learning, this would actually be a Y, so it's normally a class label, but we got started thinking of this in terms of clusters, so it's Z, which is more sort of latent variable. But basically, I want to predict this, the posterior of this class label for the n+1 sample. So the n+1 is my new patient sample who arrives. Given the lab test I'm going to make about them, which is xn+1, this vector of data, and all my sort of historical data that I've used to build my predictive model. Now, if I'm being a proper Bayesian, I come up with some posterior over the model parameters theta, and then I average my predictive distribution over this. Being lazy and slightly short for time, because we only started this project a few months ago and trying to get it done in time to make a paper, we typically do this in a point estimate, right? So I use my historical data to come up with some inference of the parameter theta. I then take some nice posterior summary of that, so like a posterior mean estimate. And then I come in and say, okay, what's the posterior distribution over classes of my n+1 sample, given the new sort of laboratory data, which is x, and given my point estimate of this parameter. In the rest of this, we're going to drop the dependency on n+1, so I'm always looking at the new patient who comes in, and I'm going to drop the dependence on the model parameters, but they're always there. So the key to thinking about this is, okay, I have for each patient or each sample, I could measure a sort of high-dimensional vector x, right? But I only want to measure certain sub-elements of this sequentially to make a diagnosis. And so what we do is we essentially partition this vector up into these elements that are either xu for x unobserved, so I don't know the value, or xo for x observed, so stuff I already know. There's no constraint here that I have to observe anything. When they arrive, I might not have observed anything at all. And obviously, if I only have one unobserved element left, I don't need to bother doing any strategy to work out which to pick. And another final bit of notation is I'm quite often interested in a single index of the unobserved features that I basically want to optimize over. So I want to pick this G, pick this element of the unobserved data well in that it's going to be informative of my final class outcome. So this is probably the most boring slide of the talk, and I apologize, but the question is, well, say I just have my observed data. Say I've observed some partial subset of the possible lab tests, say I could do for a patient. Can I still make sort of rational inference about the sort of posterior over classes? And what you can show in 3 lines here is that the posterior of the class distribution given a sort of subset of observed data is the same as the posterior given the full set of data, the observed and the unobserved data on the bottom line here, but averaged over the distribution of unobserved data given the observed data. So I'm still, in a sense, making rational decisions, just sort of making decisions based on a subset of observed data. Okay, so then we come to our strategy for doing this search. So which of these features should I measure next to make my posterior informative? So the basic idea is, given this partially observed set of features, so again the blue here, and the probability model that links the features to the classes, I want to pick the next one so that the resulting expected entropy of my posterior distribution is minimized. So the key to look at this is, if you look what's inside all the brackets, this is the posterior distribution of Z given the data I've observed and a single extra feature that I'm going to look at. And I really want to look at the entropy of this, and when the entropy is minimized, I know that my posterior distribution is very peaked around a value, so it's very informative. But the snag is I don't know the value before I measure it, so I have to use my model to take an expectation or average over that value, which I do with respect to this conditional distribution of a single unobserved point given my observed data. And then I'm going to do search over this, and I'm going to take pick the index that minimizes this expected entropy. And this is my search strategy for looking at it. And we call this the expected entropy of posterior search, or EAPS. And so the first thing is, this is quite an intuitive reason for doing this as a search strategy, right? I'm picking my next feature in order to maximize how informative the resulting posterior will be in expectation, given the model that I've previously trained. And you can show that this is an optimal strategy in a KL sense. So basically, if I imagine my sort of partially observed posterior given just the observed features, and the posterior that I have if I measured everything, and one way I could think of this is, well, I want to pick the next feature, so my posterior, after I've measured it, is as close as possible in some sense to the posterior given all the data, if it was there in expectation. And what you can show is that this objective of looking at the expected value of the entropy actually upper bounds this expected value of the KL divergence between the full and partial distributions. So you can basically show that by decreasing this, by doing this minimization problem, you're minimizing the KL divergence between these two distributions. All right, so a sort of brief example on some simulated Bernoulli. It's really sort of binary feature data. So if I imagine I have a set of classes along the columns here and a set of features that are the rows, and I can imagine, so in a diagnostic setting, each class is going to be a disease, and each feature is going to be a lab test I could possibly do. And I have a 1 if I have if lab test A is associated with disease 1 and 0 otherwise. So this is my underlying probability model. I then have some sort of false positive and false negative rate. So the generative model here would be for each patient that comes in, I sample a class, which is equivalent to sampling a distribution, and I then gives me one of these columns, and I then take a noisy observation of this column with some corresponding false positive and false negative rate that aren't necessarily symmetric, but we sort of make them so here. So you can apply these search strategies to this. So this is simulated data, so we know the right answer always. So the y-axis of these plots is what's the posterior probability of the true class given the data that I've just that I've observed so far after a small number of acquisitions. So the x-axis here is the number of features I've measured so far. And we have two noise cases. So in high noise, I have very high false positive and false negative rates, and in low noise, I have very low false positive, false negative rates. And you can see that very quickly, particularly in the low noise setting, I actually reach the posterior I would have with sort of 5 or 6 features without measuring the remaining sort of 14 or so. In the high noise case, I never reach sort of posterior probability of close to 1 because it essentially becomes an underdefined problem. But you can see when you benchmark against sort of competing strategies, it does really well. So the ones we compare against are what we call maximum posterior difference. So I basically pick the feature that gives me the biggest gap between the most likely and second most likely classes after I've done the acquisition in expectation. There's another strategy you consider called maximum variance, where I basically take the row variances of this sort of class by feature matrix and rank my acquisition order dependent on these row variances, with the intuition that if a feature is informative, it's going to be highly variable amongst classes, and if a feature is non-informative, it's going to be have very low variance between the classes. But all right, this is a very, very sort of small and silly example, so we were keen to sort of ramp it up and get more realistic things going for disease diagnosis. And so the model we have here, which is for sort of real continuous valued lab tests, is that given I assign myself to disease K, so given my disease indicator variable Z gives me disease K, then my sort of observation model is a mixture of multivariate Gaussian distributions. And there's a few appealing features about why you would want to have this as your underlying model. You can basically get sort of, not arbitrarily, but you can get very complex distributions by increasing the number of mixture components in this thing, particularly when you're modeling dependencies between them. One of the issues when you move away from the sort of binary model is you no longer have analytical entropy, or rather you no longer have the analytical objective. The entropy is still analytical, actually. So you have to do a sort of Monte Carlo Monte Carlo estimate of this expectation here. But the really nice thing about this model is that I can model very complex posteriors, but I can still analytically sample from this conditional distribution that I need in order to evaluate this loss function. And you do this by a 3-step process, which is fairly simple. I sample a sort of class label from my current posterior distribution. Then I sample a mixture component from a variable that has a very long derivation, so I won't go into it. And then I can finally sample this conditional distribution, again with sort of meaning covariances that are using the standard tricks of Gaussian distribution manipulation. So we applied this to the differential diagnosis of pneumonia. So there's a very nice database called the MIMIC3 critical care database, which is all about ICU admissions, I think somewhere in Massachusetts, actually. And we're interested in differential diagnosis of pneumonia and pulmonary embolisms. So these are both conditions of the lung that are quite hard to diagnose when they first present. They both present with lung pain. And after that, it's very hard to discriminate between them. So we used the MIMIC database to get this data for about 1,400 patients, split them into train and test. For some reason, my test has disappeared, but it is there. We picked 30 clinical laboratory markers. You run into problems very early with real sort of medical data in that most of it's missing, and when it is missing, it's not missing at random. It's often missing dependent on your final diagnosis. So we tried to build this sort of set of 30 consensus clinical laboratory markers that are present in almost all these samples. So the missingness rate for these 30 is very low. It's basically the sort of set of standard blood works you might get when you go to the ICU. We set C equals 3 mixture components in the previous model, and then we do this low-rank factorization of the covariance matrix just to save in the number of parameters model, because you end up with quite a lot. And to my absolute surprise, this actually did not bad. So it gets a test AUC of about 0.72, which you might think is absolutely terrible, but given its real data in a very challenging diagnosis and using only 30 routinely measured markers, it actually does very well. But anyway, you can apply the EAP strategy to this to see, well, how many markers do I actually need to measure of these 30 to get a reasonable diagnosis for this patient, given the best diagnosis I can get is by AUC of 0.72. So there's always my search strategy is never going to do any better than the probability model that I put into it in the first place, is the huge caveat of all this, but it's kind of unescapable in general. And you can see that actually if you do the EAP strategy, which is in blue there, you very, very fast reach the posterior you would using all the data. So this is normalized. So the y-axis is the posterior probability of the final class after I've had all the data divided by the posterior probability using the partial data. And the thing I forgot to mention earlier is because everything is multivariate Gaussian, it's trivial to evaluate these likelihoods for subsets of data, right? So I can always evaluate any posterior after a small number of observations. So this works pretty nicely. The really cool thing you get out of this is what we call diagnosis trajectories, where basically, so this is colored by the loss function, which is the expected entropy of posterior here. But you can show that the model says, well, first I should measure PTT. And once I've measured that, I go and often I measure creatinine. And then once I've measured that, I go back and measure PT and so on and so forth. And you can see the entropy of this posterior distribution dives very, very fast to the sort of final value after only a few measurements. And what's nice is basically a sort of search strategy that updates. So the first item is always the same for every patient because I haven't measured anything. But then once I've measured that, it goes off and requests a different feature and requests a different feature and so on and so forth. All right. Are we doing OK for time? Ish. Right. So I've got equations in the wrong order here. Anyway. So the then question is, well, can I extend this framework to black box models, right? So I've basically so far constructed this, contrived is the wrong word, but a very specific model that is quite complex, but it also allows me to do nice sampling of the conditionals to evaluate this bound. So the question then is, well, if you come along and you say, okay, I have this really nice prediction model, that, something black box, like a neural net or a random forest or whatever, and the outputs of which approximate the posterior over classes. So what I'm envisaging here is something like a neural net with a softmax final layer, so I can get a normalized probability of each output at the end. So if you do this, can I apply the same search strategy with just the black box function? And the issue with this is I come with two new challenges, right? The first is, how do I evaluate F for a partial input? So I need to be able to evaluate F if I've only observed some small section of it. But there's no way I can possibly train an F for every possible combination of input, right? I have like 2 to the G possible inputs. So firstly, how do I even evaluate this for partial inputs? And secondly, how do I take the expectation of this with respect to this conditional distribution of unseen given seen, given I have no access to the sort of underlying probability model that links all these classes? And so we do a slight sort of, I don't want to say hack, but it's not far from one, where I basically invoke this conditional mixture of multivariate Gaussian models to do sampling from the conditionals and assume that this, I should really have a pointer, but I assume that this basically, if I marginalize over outputs from my black box function correctly, will give me something analogous to having sort of evaluations from it marginalized over unseen values. And this basically means you have this form of your posterior search where I have two expectations. I basically sample a single unseen index, given what I've seen so far, and then I take the entropy of this, but the black box function I've seen, I then marginalize over the rest of the unseen stuff, given the seen stuff and the thing I've just sampled from. So it's quite a nasty objective function it becomes, which becomes really apparent when you look at it like this. I basically take a high-dimensional expectation, and then I take a function of that, and then I take another expectation. But it turns out that if your conditional multivariate mixture of Gaussian approximation is fairly good, then you expect the predictions from this to be roughly the same, or at least correlated with your black box model. And you know the analytic expectation of this because you know that if I marginalize over what I haven't seen, it's the same as evaluating my multivariate Gaussian distribution by just dropping the corresponding rows and columns. So what this basically does is allows you to construct a control variate. I don't know if most people are familiar with this, but I can use my conditional mixture multivariate Gaussian models to construct a control variate for this expectation. And what's good about this is that I already have to do this to fit the conditionals anyway. So I get it for free in the sense that I don't need to do any more fitting. I get it for free in that I just need to do a bunch of evaluations of multivariate Gaussian distributions, however expensive that is. All right. So we did one final application, septicemia. I won't go into too much about why it's an important problem, but it's a very, very tricky diagnosis, especially with standard assays. And the outcome of these, your mortality if you're diagnosed with them, is very, very contingent on the subtype. So again, we grabbed this from the MIMIC database, around 800 patients ish, and again, 36 laboratory features. So these are routinely measured features like blood works and so on and so forth. We sort of hammered this with a 3 hidden layer deep neural net, which works surprisingly well given it's quite a small data set. So you get an AUC of about 0.75, which again is really not bad given how hard a prediction problem it is and the sort of subset of features you're using to do prediction. And of course, we have to co-fit this Gaussian model to give us conditionals and control variates. And you can sort of see, I wasn't a huge fan of deep neural networks before I looked into this, but you do get a considerable increase in predictive accuracy, although it's still not junk yet. So one question is, well, how good is this approximation? How good can I model conditionals from one model while my predictions come from an entirely different black box model altogether? And this is a bit like saying, well, if I just had the observed data, if I were to train a new model only in the observed data, could I get the same predictions as this from taking my model that I trained on all the data and did the expectations, did the averaging over using the different model of conditional multivariate Gaussians? And the answer is you do very well. So you basically, if you compare them like this, they're rather uncorrelated, whereas you can get very nicely up to whatever noise in your data, correlated predictions by doing this averaging using an entirely different model, which is very, very cool. All right, it does well is the answer. So if you actually apply EAPS using all this control variate machinery, the funny thing here is you actually need to invoke this machinery just to evaluate these partial posteriors for this random search, but it seems to do very well given the data types. All right, I'll just briefly mention the extensions to this framework that you can look at. The first is item costs, right? We haven't discussed that I might want to impose a cost on acquiring each item. So I can imagine some lab tests are more expensive than others or more difficult to obtain. The nice thing about this is I can tack on per item costs on the end here, multiplied by some constant lambda. And the really nice thing is lambda is a very intuitive interpretation, which is if lambda is 1, then I'm going to spend $1 to reduce my posterior, the entropy of my posterior by 1 bit in expectation. So it gives me this nice trade-off between monetary value and information gain. The second thing is group tests. So in all the things we've done so far, I've acquired each bit of information sequentially, right? But this isn't always true. So often in a hospital, the doctor will order the set of blood works, or he'll order the, I don't know, set of something else. So you can easily extend this setting to acquiring predefined groups at once, which is important. And finally, something we haven't addressed at all is when do I stop? Do I know when to stop my data acquisition? And it's a kind of hard question. You know you always have this unbiased estimate of the posterior given the observed data, but it doesn't tell me how good my posterior is. So you could look at things like the variance in this estimate or similar. All right, I'll stop there. Just say thanks to all the supervisors and everyone, and please get in touch if you have any questions. Thank you.
Great, so I think we have an opportunity for a couple of questions, maybe while David gets himself ready. Anyone have anything they'd like to ask? I'll let you call on people as you like.
Sure, yep.
So I was wondering if the framework is able to take into account that diseases that have different degrees of seriousness, like gravity.
Yeah, we haven't looked at that sort of cost. So I think that would come into the final bit of introducing costs for. We haven't looked at sort of misclassification cost above just how informative you are of the diagnosis. But you could add things onto the objective to account for differences in severity or misdiagnosis. Hey, back.
Your low-rank matrix factorization?
Yes.
What was the cost associated with that compared to full covariance?
So I think we settled for a rank 5. So it's you basically reduce your parameter space to. Like,
right. Did you compare with a full covariance approximation?
No. No. That would be good, but I think rank 5 probably gets you there. It's fitted in Stan as well, which doesn't do great if you have a huge parameter space. So yeah. Hey.
How would you incorporate the uncertainty of a lab test in your model?
So that would come into the generative model. So you have this pre-specified probability model that links your lab test to outcomes. So in a sense, it's already represented because I mean, it's not really represented because we're doing it based on point estimates of parameters currently, but I would basically do the proper averaging, posterior predictive averaging. Now, that takes into account the variance in what I've measured. It doesn't give me an underlying uncertainty in the lab test, but I mean, I don't think anyone does it anyway, but you could easily include another observation model that says, okay, this is the outcome, and then you have a latent value of the actual lab test given what you've measured that you'd have to sort of do inference on from some additional data. Hi.
Yes, these days there's a lot of interest in interpretable machine learning, explainable machine learning. I was wondering if you've thought about that in relation to your models, and if you have anything to say about that.
Yeah, so you can look at it, if you imagine the data is an image rather than, so I'm doing image classification, so my features are pixels rather than disease tests. It's a bit useless, but it's quite interesting. So if you applied the same framework to that, you would train it on some image data set that has dogs and cats and whatever, and you would give it a sort of blank image, and you say, okay, what pixel do you want? You could ask the model, what pixel do you want to observe first? And it would say, this pixel, which is the most informative one amongst all the discriminating classes. And then you'd measure that, and it'd say, okay, now I think it's a dog or a cat. And you'd ask it, what pixel do you want to measure next? So that's the analogy if the data is image data rather than disease data. I'm not sure it's particularly useful. It'd be very expensive, but it'd be quite fun. But that's where this would fit into interpretation in the traditional sense of understanding black box.
Right, but also like explaining why a specific test is better than another one, for instance. A doctor might want to say that. Or
yes.
Want to say this.
It would just.
So for instance, the uncertainty, as you was mentioning, of a specific test.
Yeah, it would only say that this test will make your posterior more informative. In the same way, if you measure this pixel, it will make the result. I don't think it would unravel any more interpretation than letting you access sub-features and ordering them, essentially. Hey.
Have you given any thought to including that, basically the pseudo-optimal curve of time to diagnosis and cost to diagnosis? Just because at one end of the spectrum, you should just run all 30 tests at once. I just want to figure this thing out, get all the information you can, And the only downside to doing that is it just costs a lot of money, right? So presumably, and then you could sequence things, so you'd avoid half the tests, but then you'd have to kind of wait, and so different results, they probably all come back at different times, and they might have these windows which actually overlap in time, just because it has to get sent off to some lab for diagnosis. So any thought on that crazy complex view of the world?
Yeah, I hadn't thought specifically on that. What I had thought instead is you can maybe optimize the time at which you do the test. So you often have a clinical setting where you measure a test and it's borderline, and the doctor might say, oh, I want you back in a week and we'll see if things have changed. So if I have a nice temporal model of disease progression, I can then optimize. And the same thing, it's just a continuous optimization then rather than discrete. I can then optimize the time at which I want to do the test. If I have a nice model of how these things, but I hadn't thought in particular of the sort of lumping them together based on some cost. But that's interesting as well.
I'm going to cut it off there so we have time for our next speaker. I actually have 2 questions that I want to ask myself, but I'm not going to get to ask my questions either. So I sympathize with all of you. Hopefully you'll be available afterwards for people who still have things to ask. And in the meantime, let's get to our... Good point, all of you. Let's thank our speaker again. And then let's get to our second speaker and co-organizer of this very seminar series, David Poole, who is a computer science professor. He's been working on AI since before it was cool to work on AI. In fact, he might have been working on AI for so long that it might have actually been cool to work on AI when he started working on AI. Not sure about that. You know, it's booms and busts for us in AI.
Yeah, we've seen it go up and down.
So I'll give it over to you, David.
All right, thank you. I'm actually going to give a completely different talk to Kieran. It's related because we're both sort of being Bayesian, but I'm actually going to give a high-level overview of some work that's been going on for a number of years. Here's a nice quote from, oh, I didn't maximize it. It missed the bottom. It's a nice quote from Eric Bohm, who says basically, the program of the mind, there's a real world with real structures. The program of the mind is trained on vast interactions and so contains code that represents the structure of the world and how to exploit it. This code contains representations of real objects in the world and real interactions with real objects. And when you think of that, you think, yeah, this seems right about the world, but most of the models don't really talk about real objects and things. You know, they're not really very talking about such objects. And I'm going to... all right. So what I'm going to do, so what I'm going to talk about is some work on from graphical models to statistical relational AI to what we call semantic science. And I'm missing out my bottom of my screen. Hang on. My screen is there. That's got it. All right. So I'm going to do. So here's the argument we're making: is that acting in the world is gambling, and probability is the calculus of gambling. And as we all know, then probability provides a calculus for how knowledge affects belief. So that's a nice definition of being a Bayesian, is how what we observe about the world affects what we believe about the world. And we all know famous Bayes' theorem, of which we're happy to do here. We have the probability of some hypothesis given the evidence. But we're ambitious, and so we want to know what if the E is the patient's symptoms and history. So it's everything we're in the electronic health record, and would like to do is the effect of a particular treatment on a patient. What if these the electronic health records for everyone in the province? It's sort of, if you're Bayesian, you sort of want to predict condition on everything in the world. What if E is everything known about the geology of Earth? So this is the sort of thing we're trying to incorporate every piece of knowledge that we possibly can, and that's what we're going to try and do here. So E should be everything in the world. All right, so as the examples of decision making in medicine, what we'd like to do is we'd like to output some top diagnosis, some suggested tests, some suggested treatments, as Kieran was outlining. The inputs of this are the patient's complaints, why they've come in, the receptionist and doctor's observations that are all very high-level things, the whole electronic health records and all test results. They're the sort of inputs that we'd like to make in here. We'd like to condition on all of these. We also need to know the patient's preferences and utilities. What do they want? How much pain are they prepared to put up with, what's the costs associated with things. And also we have to worry about standardized vocabulary. Once you start having patient history about very complicated ones, we need to worry about the fact that there's that people use standardized vocabularies and they mean what they say. There are best practices, there are latest research results we'd like to, and somehow we'd also like to use all the everyone's learned things, we'd like to learn the data from every other patient. And so what we'd ultimately like to do is like to make decisions conditioned on all the information in the world. We don't know how to do that, but that's what we're trying to get to, so that's what we'll talk about. There's a whole lot of problems with these things. The effect of a particular patient is the data is heterogeneous. There's lots of different sources, lots of multiple points in time, patient reports, receptionist observations, X-rays, lab tests. And we'd like to combine these heterogeneous data sets. Again, the knowledge is provided because it's unusual that patients don't tell you everything about them. They tell you what's weird about them, right? And it's not sampled at random. It's provided because it's unusual. At multiple levels of abstraction, and often you actually have knowledge that people tell you things at high levels of abstraction in terms of more general terms, and also multiple levels of detail about parts and subparts. So we'd like to combine all those things together. And some of the examples I'm going to do is predicting in geology. We can predict the amount of minerals at a particular location, or predicting whether a person would like an apartment, or all sorts of things are in this framework. Okay, so the problem is inherently relational. There are lots of objects, there are patients, body parts, tests, infections we'd like to talk about and relations amongst them. There's uncertainty about relations, about the identity, about whether something exists or not, and things that don't exist don't have properties. You might have a property of some disease, but they do not have a disease, and all sorts of things we want to talk about. We need standardized vocabularies. If you look at electronic health records, a lot of them use this SNOMED-CT as a big ontology of medicine. There's over 300,000 medical concepts. That's sort of an interesting number because once you square it, you get more than the population of people. So what happens is the data is inherently sparse. For almost every pair of diseases and almost every disease treatment pair, no one in the world has it. Right? We're not going to learn interactions amongst these things because there's not enough people in the world. Right? Even if you had the electronic health record for everyone on Earth, we still won't have enough information to learn these interactions amongst diseases. So it's a challenge that we need lots of, we're going to have priors in these things. There's lots of experts and textbook knowledge may be wrong, and we want to do in here, so that's the other challenge that we have. And we want to use whatever evidence we can get to learn from experience. We need to justify recommendations, as one of the questions was. And we always want to base decisions on the best available evidence. We also want to make sure that we're also asking that question. And we also want to have things like transportability, as you're going to learn in Vancouver and apply in Beijing, because we don't have good data about things. We'd like to make lots of assumptions about how the world works. So PubMed is where medicine's published. 10,000 articles are added each week. I mean, it's the amount of literature that's coming in, the amount of knowledge that's coming in is ridiculous. IBM Watson proposes to read the literature to provide evidence-based advice for specific patients. However, if you talk to people, you're going from data, people have data, they make hypotheses, they write research papers, then they misread them, and then they're applying them to the clinical practice. If you ask doctors or people or other about this, they're horrified at this fact of Watson misreading what they're writing. So wouldn't it be better to have the research published in machine-readable form? So we're trying to get hypotheses that are published in machine-readable form. So some of the examples I need later, we actually have models of all the published, we have hundreds of models of people who predicted landslides, for example. We have lots of models of, in geology of where you can find different minerals, and sort of people are writing from published data, we're trying to get representations of them. All right. In geology, they're similarly, we need to make decisions. Interestingly, geologists know they need ontologies, they know they need standardized vocabularies because geological maps do not match at national boundaries. The geology sort of changes, if you look at geological map, the geology changes across national boundaries and even between provinces because they don't use standardized vocabularies, and so more and more, so they know they need to use ontologies to make sure that we can actually interoperate. Otherwise, you don't get much data, right? Otherwise, if Alberta used a different vocabulary than BC, which they used to, you can't interoperate. We can't sort of combine all that data, so we have to make sure that we can combine them. The European Union is currently forcing people to all levels of government to publish all spatial data with respect to some predefined vocabulary. So it's nice to be able to understand what's going on here. All right. So what I'm going to do is I'm going to give two short parts in here, one of which is an overview of some work on statistical relational AI, on relational probabilistic models, and then we're going to talk about what we still can't do. So this is some work about statistical relational AI. So statistical relational AI is this sort of subfield that started with sort of probabilistic logic programs in the early 90s. We're building probabilistic logic programs. They're interesting logic programs because they extend relational databases as well as they're Turing complete. So these were sort of early probabilistic programming languages, and they also naturally generalize Bayesian networks. Then there was work in the 2000s, particularly with undirected relational models, and now there's lots of work on relational embedding models that are more inspired by neural network type models. So the first order predicate calculus. I'll skip it. So here's one way of viewing what we're doing is you can get the first order predicate calculus by adding on the propositional logic. We can have logical quantification and variables. So you can talk about for all x and there exists an x, and we can have relations amongst objects. So we can have sort of a likes relation or something like that. We could have a relation that's about test results. We can also start from propositional logic and add measures over possible world and conditioning. We end up with probability, and which the relational probabilistic models we're doing, we're trying to combine both of those two. And so what we can do is we're trying to combine both the predicate calculus and probability theory. So what happens in here is if you think about machine learning, you typically have features of the world, you can they're meaningful. But if you actually look at most relational databases, the names are in there as names of objects, they're names of individuals. And so what we'd like to do is to not have informative feature values, and it's the property of the individuals and the relations that need to be learned. So here's an example of this. If I have some students and courses, and I observe this student on this course, and I'd like to know how this student, so here's the whole lot of students, of course. These are just arbitrary names, C1, C2, and the students are just arbitrary names. There's nothing about them. They're not like things we can learn, from what we normally think of in machine learning as we're learning these things. These are just names of things, and the names don't matter, right? It's only the relationships among them. Turns out you can actually use, if you want to predict how this particular student's going to work on this courses, you can actually, from these, you can do some probabilistic modeling to actually work out that it's likely that one of the courses is harder than the other one based on how people have gone in here. So we can actually do probabilistic reasoning. We don't need the features. We can reason about the objects and relations. So here's a here's a Bayes net representation of that. And what happens is that there's a random variable for our model says here there's a random variable for the intelligence for each student. There's a random variable for how intelligent that student is. There's a random variable for the difficulty of each course, and the grade of the student in the course depends on the difficulty of the course and the intelligence of the student. And then we have a great big graphical model now, and we're going to share the structure of these things. We're going to say the probability for all students and courses, how this grade of the student in the course depends on the intelligence of the student and the difficulty of the course, and we've got this sort of parameter sharing. So we're going to have parameter sharing in here about how this is working. There's code in here. And so what we're going to do is this, often the nice thing to do is this sort of plate notation. We're going to write Bayesian networks with populations around them. So we're going to have S and C are logical variables. And then these are going to be random variables. And there's a whole lot of random variables. For every student, there's a random variable of the I of the S. For every course, there's a difficulty of the course. And for every student course pair, there's the grade of the student in the course. And we're going to observe the grades, and we're going to work out the, predict the difficulty of courses. Okay. And this can, small models, this model here with 1,000 individuals, 1,000 students, and 100 courses has, 100,000 variables. Has 100,000 random variables because there are all these interactions amongst them. But there's only you need a few numbers to specify these models. All right. So the trick we're going to do is individuals about which have the same information should be treated the same. So what we're going to do is we're going to exploit knowledge, we're going to exploit features of this, but they're just meaningless names. And the names can be exchanged and the models don't change. And so now we have, so then there's a whole lot of work which is about lifted inference. And so instead of reasoning at the random variable level, we're going to use lifted, we're going to actually reason at this higher level of work. And we're going to just count over those individuals we're not distinguishing. So if you want to work out what the probability of someone committing a crime is, it depends on how many other people there are in the world. And we don't need to model all of them. We can actually just count how many there are because and so as we don't distinguish people, we can actually do much better. So there's work in there. And it turns out this is one of the very few areas of where we can really have huge improvements. If you can show that if the lift ground is polynomial, we can do it in logarithmic time. If we can go from exponential to polynomial in the number of individuals from any class of models, and we can always do exponentially better than not lifting. So it's one of these cases where we can always exponentially faster than grounding. So by reasoning at this higher level abstraction, we can actually do much better. All right. And then more recently, there's been some sort of tensor factorization of neural network models. And so what we can do is there's these knowledge graphs that are existing. They're databases of triples. We used to call them semantic networks, but now they're called knowledge graphs. We want to estimate the probability of some triple given this knowledge graph. And a very common, one method that actually is very old is this polyadic decomposition model. There's 2 vector embeddings for each individual and 1 for each relation. So we have this for each, there's an embedding, there's a head embedding for each feature and for each heading, and for each hidden variable, for each head of this tuple, and for each hidden variable f, we've got this embedding of this individual for this over all of the features. There's another embedding for the head, another embedding for the tail, and you multiply those 3 values, and you end up with a nice model. Unfortunately, it doesn't work very well, but what does work well is to also have an embedding for the inverse of the relation, and to learn to predict both of them. This actually works, this is as far as we know works the best of any of these models. We have a paper in NIPS this year that basically gives this model that says if you do this polyadic decomposition, but also model, because what happens is the heads and the tails don't interrelate, and you can actually end up with them not being correlated, no information about themselves. All right. So we can have these vector embeddings of this. So it turns out that they really work really well for predicting relations, but they don't work very well at all for predicting properties. And the intuition, because these are all public, there are all these people who are now excited about tensor factorization models. They somehow rely on lower dimensional representation. There isn't one for properties of individuals. So if I want to predict the gender of a person, there's no lower dimensional feature. And you actually can't, they actually don't work for this very well. People don't tell you this. So imagine trying to predict the gender of person P and the ratings, the P of M, that's trying to predict the gender, the person P, and the ratings of each person in each movie. You'd like to predict both ratings and gender. And one of the embeddings so each person has a big embedding for them, but you can just memorize gender. And it turns out that there's sort of too many parameters to make this work for predicting properties of the world, and it sort of fails to do this. It's sort of interesting that these things can predict relations, but they can't actually predict properties of the world. So one of the things that we did was in AAAI last year, we had this sort of relational neural network. So we're going to have feed-forward differentiable models about these things. And in one of these things, like this one here, that says this hidden unit of a user depends on what movies the user rated. And this is sort of a logistic regression model. Inside of here, we're learning a specific hidden property of movies, and then we can aggregate over them. So we've got to count over them to learn general properties of users. So there's this models, there's this whole realm of models that are now people are working with that are trying to learn relations. Okay, so what I'm going to do in the last 5 minutes I think I have, I talk a little bit about what we're trying to do when we're mixing up what we call semantic science. And so what we're going to do here is we're going to talk about, so here's the picture I like to draw. We have ontologies that represent the meaning of symbols. We have data that depends on ontologies. We have hypotheses that depend on training data, and then we'd like to make predictions about new cases. And all of these are going to evolve in time. And what we'd like to happen is that people are going to publish hypotheses as well as publish data. And so we've been publishing mainly data in mainly hypotheses in geology that interact with data in geology. So in philosophy, ontology is a study of existence. In computer science, an ontology is a specification of the meaning of the vocabulary used in an information system. And there are these enormous ontologies that exist. We have a geology ontology that has these thousands of minerals, but SNOMED CT has 100,000 different clinical findings, different terminology that are used in electronic health records. So in the ontology, there are individuals, classes, and properties. And what happens, the other thing you should know is, so when we define it, we define what are the classes, what are the properties, and then there are individuals in the world. And this is what we get, how the modern ontologies languages are defined. One interesting thing is that we talked about triples before. All relations can be represented in terms of triples. So you might think that if you had triples, you could do everything. So in particular, if we have this table of this row and this property and this value here, we can represent as this triple of the row, the property, and the value. And Ri becomes what's called a reified individual. This turns out this is true, but it turns out if you there are things like marriages and bookings and lab reports we make into objects that we can talk about. However, each reified individual has a very limited data to learn from. There's only one value for each property, so they're very sparse. There's very little data again when we talking about lab reports, so if we want to make them very heterogeneous and just talk about triples, we actually have to model things in different ways. So Aristotle talked about them. I'm going to skip over that for a second. The other part of this is data. Real data is messy. There's multiple levels of abstraction and multiple levels of detail. In the ones we're doing, they're on vocabulary from lots of different ontologies, the rocks, minerals, and the top-level ontology. And there's lots of metadata that make a difference. So people publish, part of it is publishing this metadata that we'd like to do. So here's the sort of data that here's my observation. This is one I condition on. Here's a map of the slope of how sound is there. This is the Cedar Sky Highway goes up here. This is just north of Vancouver near Squamish. And this is sort of one of the observations we'd like to do. One of the observations you'd also like to make is one of slope, of structure. This is faults and folds. So this is the sort of observation of the world we're going to make is essentially map data and objects and relationships among them. And we're trying to predict landslides in this case. So we have models of landslides. So we've got very complicated data in here. Okay, I'll skip this because I'm running out of time. All right. The other part is hypotheses. What we other want to publish is hypotheses, which are just programs that make predictions on data. And we're going to sort of look at probabilistic programs of making predictions on data. And that's how it's going to relate back to what we did before with relational probabilistic models. So and here's a hypothesis. So this is the this is the probabilistic prediction of what we did is we represented some one particular research paper. We represented the probabilistic model about where landslides were and made them predict and where we were observations of the world, and then we plotted it against observed landslides to try to work out. So this wasn't a train, this was actually representing a research paper. We had experts read a research paper, and we checked the, and we sort of represented that to make predictions. All right. So now what we're going to do is that now people are publishing more data, and now we also want to rake hypotheses that make probabilistic predictions. All right. Let's stop there. So in here, so what we have is we have a rich history of probabilistic models that build relational data, and what we're trying to do build now is ways to develop and deploy knowledge about how the world works so we can actually not only publish data but publish hypotheses, and hypotheses are just programs that predict on data. We're building them, we're trying to predict landslides, we're really using the fact that Europe is now publishing public data about everything, and so we really want to make observations not on images, not on lab tests, but on spatial data and little high-level things, so we can predict landslides and crime rates and all sorts of things. We're making predictions, and effectively we're getting so that the models that we build accumulate over time. So people are going to publish hypotheses, and you're going to say, I can do better than you because we're going to predict landslides in Italy or landslides in France or something, and work this out. So that's what we're trying to do in this case here. Right, so we're going to justify the answers with people develop hypotheses. We're going to justify predictions by what hypotheses there are, and we're going to justify hypotheses by the evidence, by what data supports them. They're going to interact in some complicated way, and we're going to develop lots of formalisms and discard them before we converge on it. But it's sort of an interesting problem that's sort of at the higher level of people are building low level, learning from individual images or learning from other things. We're trying to stick all of these things together to actually make high level decisions about society of things. All right, let's stop there. Thanks.
Right. Once again, we have a chance to get some of your questions.
Hey, thanks. I managed to spot something that talks about the superior worth of hypothesis comes from linguistics. In the slides, you didn't talk about that.
Sorry?
So somewhere in the slides, there was something about the superior worth.
Oh, yeah.
Okay, could you talk about this?
Yeah, that's a great thing. So here.
Yeah.
It says that people's perceptions and their thought are determined by what can be described in their language. So it was developed from the 1920s. I think Sophia was the first one, Worf was a student. And they said that what you can think is developed from your language. So for what we're doing there, it's sort of controversial in language, but for us it's sort of stronger, is what you can store and communicate in an information system is constrained by the representation and the ontology used. And it's really important that we understand this representation and the ontology. It's all very well for us to have our images, and we know, for example, that things like convolutional neural networks only work because of the format of you have pixels together are together in this. So if you have a different representation, of images, so for example, you have one that the first few bits represent the average color, and then you divide it up and you fade it in. So I think that's called so each model, so you have this, the first few bits represent the average color, and the next ones you say, how does this differ from the average color of where it is? And you keep going down. I forgot what that's called now. What's that called?
Resolution.
Yeah, you have multiple resolution images. Once you do this, all of a sudden, all these things that sort of are just magic to work with images don't work with this because you have a completely different representation of how you're going to represent images. We need to somehow redevelop all of the tools. You need to sit there and say, oh no, I've got a whole different representation of images now that don't, my previous methods now just don't work. They just really don't work in here. But we've got this case about where we've got so many different representations that we need to really reason about them, right? So, and so the other point here is that ontologies come logically prior to the data, and different ontologies result in different data. So as you have different ontologies, you have different data, and you have to worry about that. And the data can't make distinctions. It can't be expressed in an ontology. If you don't have vocabulary for something, if you don't tell me things, I can't. It's the data loses it, right? So if I tell you about coin tosses and I don't tell you the sequence of them, it's noise. You've lost that information. So we're getting more and more richer data that we'd like to extract.
All right, are there any other questions about the talk David gave or requests for him to give other slides that he didn't give in the original talk, as the case may be?
Yeah. Yeah, there.
Oh, hi. Thank you. You didn't use the phrase data mining. That's, I guess, the sort of first level approximation where you're making such comparisons on something that are either rows and tables or can be joined to become such. And then the other extreme, the eureka realization that benzene is a ring. There's examples of scientists waking up in the middle of the night with fabulous insights, epiphanies, which were very distant from anything that was directly observable. So should I take it from one of your earlier slides that if you set up trees of logical inferences or plausible logical inferences and chase those long enough and far enough, such insights will be the end product?
So I'm actually, two things. So I don't actually know the difference between data mining and machine learning. So I'm the wrong person to ask about. It's all data mining, it's all machine learning. The other part of it is I don't necessarily, our hypotheses, the hypotheses people publish are not necessarily machine learned ones. I want people to put in hypotheses. No, there's no hypothesis in the world that's purely machine learned. They're all a mix between prior knowledge and this, and we want to people, and the game we want to play is for people to scientists to put in all of their prior knowledge and to publish these things with benzene. They're going to publish it and it's going to make better predictions than someone who doesn't do this. So all the models we're building here are all mixes between, and you also don't have pure thought knowledge. They're all mixed between prior knowledge and data, right? All the hypotheses you're going to do it. You're never going to publish a hypothesis that's just purely from data. It doesn't exist. There's a no free lunch theorem. But you need informed priors, and people are going to publish benzene. They're going to say, I've discovered benzene. Now that makes better predictions about the world than previously. And now everyone's going to say, oh, well, we're going to throw out all the other hypotheses because they don't work well. Right? So this is sort of an overview of machine learning is sort of building hypotheses, but it's not building hypotheses automated in isolation of people. That doesn't. We need priors. We need experts. Scientists are going to be even more needed than just throwing in lots of data, right? So we're going to have. We can have models, but need people in it.
Let's take one last question. You guys can fight over it.
I have a question on the first part of your talk. You said that these embeddings, they work better on relations, they don't work on properties. So what kind of test you use to make this, to be able to make this claim?
So what we can do is you can actually, so the one we did actually, it was interesting. We had a course project that it was actually a small course, and we all did this one. We're actually trying to predict the gender of people from movie ratings databases. And so what tended to happen is you either tended to learn, if you tried to predict movies, it turns out that you can, if you try to predict both of them, you can just memorize the gender of people because it's provided, and the test set sort of didn't actually help you. But you had to force yourself not to memorize gender, even though it was actually important to, thank you, even though it was important to do this. So we were predicting, so we tested it on test cases of predicting held out gender from movie lens data sets. We were predicting both gender and trying to use the movie relations things. And
the prediction tasks.
Prediction tasks, yes. We were predicting gender from movie ratings, where we had both training and test sets. And the models that used the matrix factorization models, which this is a generalization of, so this is just multiplying 3 things instead of multiplying 2 things, they overfit to, they're too flexible. You can actually just, if you want to also model gender, we just memorize it, because remember we have a value for each user. So these were held out tests, and we went through everything that we could actually possibly think of that would work, and sort of we ended up developing these other models that made explicit aggregation in there.
All right, let's thank David again. Let me just comment in conclusion that this was a really great choice of 2 talks to have for our inaugural CAIDA research seminar, because both of them really combined cutting-edge AI, machine learning kinds of ideas, difficult probabilistic reasoning methods that leverage really modern approaches with kind of core decision-making problems that really go beyond curve fitting and really think in a non-trivial way about making decisions. And fundamentally, that's what the center's focus is really all about. So I think that this is a really nice example of the kind of variety of decision-making problems built on top of modern AI. So I really enjoyed it. I hope the rest of you did too. And I think we'll be doing this roughly monthly. Is that right, David? So I hope to see you all in about a month's time. Thanks again.